you very much for having me. And I want to tell a little more of the story that Joe was just talking about. Joe Weber actually did detect gravitational waves, or he thought so. And then there was another development. A lot of other people got drawn into it because the experiment that he showed in that picture wasn't all that difficult. You know, it was a big bar, you had some strain sensors on it, and a lot of people in the world were able to reproduce that experiment. And within 2 years, it was established that Joe was not seeing something, which was a real shame. And it put a pall on the field for a while. So let me tell you what is going on, that the other development that actually finally succeeded. And even though Barry Barish and Kip Thorne and I won the Nobel Prize, the guys who did the work and the girls who did the work are in this picture. This is the scientific collaboration called the LIGO Scientific Collaboration. It has about 1,000 people in it and about 100 different institutions. In fact, there are several in Europe that are part of this. You'll have to peruse my slides to find the various institutions. I want to talk a little bit about the science of the waves first, so you'll understand the detection. And where I'm going here is I will talk about the detector, then I'll tell you a little bit about the complexity of the detector, and then I'm going to tell you about what's first discovered, and then I'm going to tell you about further problems, and then about the future. So I hope I can get all this done in the 25 minutes I have. So here's the gravitational waves, and let me see if I can get this thing to work. Yeah, okay. The sources are non-spherically symmetric accelerated masses, and that was not established by Einstein in his first paper, but rather in his second paper, that 1918 paper. And the kinematics, which he had quite right, is that they were expected to propagate at the speed of light. And they are transverse waves. In other words, they're very much like electromagnetic waves. They do their dirty work perpendicular to the direction in which they're moving. And this picture will show you what goes on. If you can see that spot right there, that red rectangle where the yellow marker is right now, is you. And we're going to have this thing. Let's see if I can get it moving. Huh? Well, fellas, it didn't advance. Oh, dear. All right, oh, there it goes. Okay, you have to hold it longer. Okay, good. So what you're seeing in this picture is a motion which is complicated, but you'll see that it's a motion that stretches space in one dimension while it contracts space in the other. And that keeps oscillating back and forth. That's one property of the picture. The other property of the picture is that if where you're standing, the two dots that are next to you, let's say, they don't move very much. But the dots that are far away from you, they move a lot. And what this picture is at any one instant is exactly this picture that you would get if you pulled a rubber band that you had marked with a marker. And it's a strain. What's the same at any one moment along one of the coordinates is that the change in position divided by the separation of the particles is the same for all parts of the picture. The strain is the field quantity. And now, so that gives you an idea of how you might go after detecting this thing. In other words, if you put out a system that follows the same kind of motion as these dots, you would succeed with doing it. And Weber did that by having it along one dimension. He had a bar. He actually thought of it as a force. We happen to think of it more as a strain in space, and I'll get to that more in a minute. But the other thing is that you use both the fact that there is expansion in one dimension and contraction in the other. So let me take you to a little animation of what is actually done to do this. Again, this is quite slow. I'm surprised at this. There it goes. Okay. This is a little interferometer, and the way it's set up, there's a laser right there. That's a beam splitter. And these are these distant mirrors. And you think of yourself as being at that place where the red square was. That's where we placed the beam splitter. And there's a detector over here. We're going to launch a wave if I can get this thing working. Yeah, okay, good. So what you see is the red, wherever there's red, that's where the intensity of the wave is large. And the waviness is the electric field in the wave. And what you're noticing is the following. Right now, this is set up so this path and that path are equal, and no light goes to the photodetector. In other words, at this juncture, you've set this up so no light is going to the detector by having equal arms. Now a gravitational wave will come down on this, stretch one arm, shrink the other, and it makes light appear at the photodetector because you no longer have the cancellation of the two beams. The reason why I want to show this, is the basis of the entire measurement. It gets very complicated in a minute. But just keep thinking, there is no other more fundamental aspect than the fact that you've set up a system of position points in space, you've made them equal distant from you, and now what happens to the gravitational wave stretches one and shrinks the other. That's one way to think about it. So, along comes Kip, and many of us, but Kip was the one who was most influential in much of this, and he says, yes, that's fine. If you're going to try to measure this, you have to do it to a precision. When you look at astrophysical quantities of a change in position divided by position, that's the h, that's strain, of 10 to the minus 21. If you want to get anywhere, it has to be better than that, smaller than that. And at that juncture, most engineers walk out of the room. They think that you're smoking something, you know. And but let's put it into a little better context, what it really says. Oh God, okay. Yeah, what it says is that you have to measure, and I'll put it in the context so you'll understand why it took so long and why it was such a challenge. And that is that the position change you have to measure is 10 to the minus 12 of the wavelength of light. Okay? And that is if you have a path length that is 4 kilometers, which is the way we built these instruments. So you're talking about motions, I should have said that first, of the order of 4 times 10 to the minus 18 meters at the end to make Kip's condition. And that is just barely good enough. So, okay, much, much less than the wavelength of light. That turned out, as you'll see in a minute, to be relatively soluble. The one that was much harder to solve was that you can't have the mirrors, those things where there were dots in the other picture, move more than that 10 to the minus 18 meters. And that's much harder to do because there's so many other things that push the mirrors around. And so let me quickly show you the solution to making it so that you can use the wavelength. I will not describe this in detail, otherwise I won't get finished. But here then is a laser, and what you're familiar with from my first explanation, here's the beam splitter. That was where you were standing. That's where you were standing. And then there are these two distant mirrors. Now there's some new things in this picture. Again, everything is set up so no light goes to the photodetector. And for one thing, this is how you gain that sensitivity. What you do is you make the light bounce back and forth many times. You do that in both arms of the system. That's one trick, so that, for example, you'll have 300 passes effectively of the light. The other one is that you do something which is when there's no light going to the photodetector, where is the light going? That's coming out of the laser. Well, it's coming right back to the laser. If there's no light going here, there's a little bit absorbed in these mirrors, but most of it, in fact, all of it pretty much comes back. And so you put another partial mirror right here that partially transmits, and that is designed so that the light that would leave the laser and reflects from it is canceled by the light that comes back out of the interferometer, so no light goes back to the laser. That's essential. And so that then makes it so you would now have a situation where you might have 50 watts of light out of here. You might have something like 50,000 watts of light in this little cavity, and you might have a half a megawatt of light in here. And that's how you eventually get the sensitivity. This device right here is another mirror which I won't describe except to say you can change the spectral response of this entire system to the gravitational waves that are coming down. And that's very elegant, and I can talk to you guys in private about this. Okay, so now here is the disposition of all these detectors in the world. The LIGO built one at Hanford, that's in the Northwest. They built another one in Louisiana. These are big L's, that's what they look like. There's another one in Italy, near Pisa. There's a smaller version of it, which is effectively research interferometer in Germany here in Hannover. There's one being built in Japan in the same mine that Professor Kajita was talking about, and that's about to run. We'll get to that. And there's a version of it that's going to be built in LIGO, India, and I'll show you a little about what all of these things will do. Okay, so the reason why you want more than one interferometer is because, as this will become very apparent in a minute, you want to be able to determine where in the sky does the gravitational wave come from. And you can't point these detectors. You do it all by timing and doing triangulation. Okay, now, I just showed you this picture because this is sort of the beginning of LIGO, where we started these detectors in the field, these 4-kilometer ones, about 2001, and down. So you can see this is now the sensitivity in a spectrum of amount of motion, meters per root hertz. That's a noise. You can divide that by the L, that's 4 kilometers to get the strain. And here is the frequency. For example, right there is 100 hertz, and here is a kilohertz. And you can see that there was vast improvements from 2001 to 2006. We kept getting better and better and better. And finally, we got down to here. We almost got to what might have been the theoretical curve for the entire system. You can calculate how good it has to be. And it just doesn't quite make it at low frequencies, but it does cover this all. And we got what we call a very clean non-detection. Now, people laugh at that, but it turns out a clean non-detection is not easy. You have understood the system well enough to say you did not see any gravitational waves. And with that, we were able to go to the NSF and say, look, we want to build a detector that does improvements on the stochastic noise, the things that changes the position of the mirror. So let me see if I can get this to move. I may get two at once. Okay, so what was done is we had much more complicated ground noise isolation systems, for example, put into that new detector. These are pendula. Here's that very precious mirror which has to sense the gravitational wave, but it's hung from 4 pendula. I won't describe this, but this is a very elegant device that can be used by other people, where you have a servo system up here that cancels the ground motion, and you hang that pendulum from it. So that's an active vibration isolation system. So here's what we saw with this system. This was the first detection. And what you see in these pictures is that this is a time series. This is time here. In all these pictures, the time is the same. This is about, here, 0.1 seconds is that distance between these two. And this is the signal seen in Washington State, and this is the signal seen in Livingston, Louisiana. And this is junk. And it slowly something emerges out of the junk. And by the way, the amplitude is not far from what Kip suggested. This was a huge signal. This is 10 to minus 21, the units, and this is sort of 1. So right here at the end of this thing, it's around 1 times 10 to minus 21. Unbelievable that Kip was that close. This is garbage. That's garbage. And this is the same signal now seen on superposed. The blue is now the one that's superposed at Livingston. And you had to delay this signal, the Livingston signal. You had to delay the Hanford signal with respect to the Livingston signal so they could be on top of each other by about 7 milliseconds. And so now, and by the way, this whole signal was, and this was not in the original paper really, it was filtered by a thing where this is the frequency, and it was like what you have on your audio set. A low frequency filter to get rid of the rumble, and a high frequency filter to get rid of the hissing noises, and that's all the filtering that was done to see this. It was huge. And this is, with those filters, the theoretical waveform, if you made this 2 black holes, and we'll get to that in a minute, of about 30 solar masses. You get a numerical relativity solution, which is a whole other miracle that took place. That numerical relativity was finally at the point where they could make real calculations of astronomical systems. And these are the 2 best fit. Yeah, I see what happens. This goes out after a while. So anyway, this is one way to look at it. It's a time series, and why it has this funny shape is because of this filter. But down below it is a different way of presenting it, which you'll have to get used to. And this is the frequency of the signal as a function of time. So this is sort of a sonogram of it, and you can see that the color is the brightness of it. And this is the signal at Hanford. This is the signal at Livingston. And you can see it's a chirp. I don't want to play it for you. I can't quite sing it. But now what happened is this was the first detection. We didn't believe it. We published it after a lot of soul searching, and you'll see in another region we had tests. Before we published it, we had detected some more of these. Otherwise, we wouldn't have done it. And this is what it was. This is now without the filter in. That's why this is the theoretical waveform. And this is what it is, 2 black holes, and you'll see the parameters for it in a minute. And at this point, they collide with each other, and then it's quiescent. And this is the theoretical signal that you would get using numerical relativity. And there's some gee whiz things about it. They're right down here. For example, this is the velocity as a function of the tangential velocity, and it's getting up to 0.6 the velocity of light, and so forth. So this is quite an interesting thing, and it turned out to be 2 black holes. And here is what we saw in the first days of LIGO. And, okay, I just don't want to hit the wrong button here. Okay, yeah, so, yeah, this is that signal. Now we have it in another way, writing it here in terms of the time. And this is the first signal that was seen, the one I've been giving you the story about. A little bit later, and these dates are, September 14th. This is October 12th of that year. That one we weren't so sure of. Here's the one that convinced most of us. This is the day after Christmas. And this thing was a completely different set of things. Here are the parameters that are associated with these. This mass was 36 of one of the black holes, of solar masses, 29 another, and it had lost 3 solar masses of energy in the process of making the new black hole. And so, by the way, there's a very interesting number that's associated with this we'll get to, but I want to leave it. These are the others. They were smaller. And but let me get right to this. If you put that, this is a way of imagining what's going on here. If you put this thing at one distance, you put it at the distance of the sun, this pair of objects, you would get a strain at the Earth. That's the motion. The strain at the Earth would be about 10 to the minus 6. In other words, you would shrink by a micron, or by a couple of microns, and expand by a couple. You would never sense it at all. But the energy that goes through you is unbelievable. And, oh boy, okay. I can't get the thing to show it right now. It's 10 to the 25 watts per meter squared. That's an incredible amount of power. I mean, the sun in light puts out about 10 to the 3 watts per meter squared. This is 10 to the 22 times higher than any, it's just enormous power. So that was a very big deal. And then the big thing that happened a little bit later, a year or so later, or actually a year and a half later, is that the Italian detector came on the air, and now we had 3 detectors seeing it. So here's LIGO. It's the same kind of thing. It's another black hole system. This one is sort of 30 solar masses and 25 solar masses losing 2.7. And here is the Hanford, Livingston, and here is the Italian detector, not quite as good, but you could now locate where it is better. And now you had a region in the sky which was sort of 10 square degrees, still very big, but for an astronomer. But now you had something where you could tell an astronomer where to look. And that was supremely important. The next one that we detected, and we detected more, but this one was the one most spectacular in the sense of what it meant for science at the time. I think the black holes will be very important, but this is something else again. What this is we saw this in 2017. And what it is now, I hope you're a little bit familiar with this looks very different than the black hole. Here's time, this is 10 seconds from here to there, and this is now the frequency. I'm only showing you the frequency curve, and it makes a beautiful chirp. And it then goes off into, it goes up higher where we don't have enough sensitivity. That same thing was seen by a gamma ray telescope. And that's the gamma ray telescope. It saw it about 2 seconds later, 1.7 seconds later, there it is. This is the end of that chirp. It was seen by another channel on that same gamma ray telescope, and still another gamma ray separate satellite saw this. And what this was is 2 neutron stars colliding with each other. And that set off a whole, it set off an entirely wonderful search, which consisted of this. Here's sort of the error bar of our error bars. Let me start with the LIGO error bars. There's a banana down here. This is a picture of the sky. And here is then the business of just LIGO alone. Here is if Virgo, which is another detector, that one in Italy, was running. They didn't see it, but we knew if they had seen it, they couldn't see it because it was on a location in the sky where this detector was insensitive. And if you interpret that, you could then say the error bar for the whole thing is about this small green area. That was enough to have it identified with Fermi, what they were seeing, and then eventually, about 10 hours later, there was an object seen using ground-based telescopes, which is NGC 4493. It's some 140 million light years away from us. And here, a little before this event, this is this galaxy. There was nothing at that point. And after the event, people took pictures of it again, and there was a new bright object right about there. And that was this 2 neutron stars colliding. And that has set off a tremendous piece of science. In other words, now that we have an identification with a real telescope, we can have a position in the sky, you can establish that, where it is. We know where it is. It was first seen by the gravity waves, but then it was seen by all the other astronomies. And the model of it is pretty much what's on this picture. Here are the two neutron stars. They make themselves into a black hole. You're not looking at the thing. The detector wasn't looking at it exactly along the the direction. It was 5 degrees off, and you would get those signals that we saw. And on top of that, all the optical signals and infrared signals and all the different astronomies had something to say about this. And that was a big discovery for all of astronomy. And here are some things that came out of that. One of them I think that came out of it is that if you look at the periodic table and you do the modeling of what those two neutron stars, when they come together, does, you find out that you will get. These are the color coding here is the periodic table, and these are the different mechanisms. For example, if you have two stars that they collide with each other, but they're not massive, these are the color codings in the periodic table. It turns out this thing had two merging neutron stars, that's what they are, and you should see, for example, that there is lines that come from all of these elements, and in fact, probably it's a place where you make a lot of platinum and gold. People got very excited about that. So anyway, that was a discovery that was one that X-ray astronomers saw, gamma-ray astronomers saw, radio astronomers saw also. And here is one of the interesting results that came of that. There are many interesting results. This is one of the mock-ups. This is a picture of the value of H0, which is the expansion constant for the universe, as a probability. And this is for three different, there's the green one is Planck, which is a superconducting satellite that's looking at the cosmic background radiation. Here is another one. This is now the measurements made by Weiss, who's going to be talking in a minute. And where that fits, there's already a discontinuity between these two. This is the mass of that device that is doing it. And there's a discontinuity, which is probably real. But here's the thing that gravitational waves would have come. If you said, you know the distance to it, and we knew that, and we know the strain signal, you would predict the curve of probability of that this makes a neutron star binary system have an ellipticity, which looks just like that curve. And that's just nicely between the two X-ray curves. That's just a sign that if you get more and more of these, the gravitational wave detections will play a big role in starting to look at the universe as an entirety. That's a big step forward. Okay, another thing which came of it, has not yet come of it, but is looking, for example, at the oblateness of these two neutrons. This is in the future. This has not happened yet. But, for example, you will see in the gravitational wave signal, which I have to be careful to hit, you'll see a delay because the two stars become somewhat elliptical as they get closer and closer, and they pull a tide in each other, these two neutron stars. It'll change the waveform. That's something we can look for as a gravitational wave phenomena. What was not seen in the first detection. Let me see. Yeah. The other thing you can look at is once the two stars have collided together, there's a big mush of nuclear matter. And that has normal modes of its own. And that's in a sort of tenth of a second. And that's been calculated, and it's something we clearly would be able to see. And they make signals that are high-frequency signals, sort of in the kilohertz to 3 kilohertz. These detectors are sensitive for that. And these are different models for the equation of state of nuclear matter. But you can see that's what these waveforms look like. And here are the spectra, and they stand up above the noise of LIGO itself by a factor of 3 dB or something like that. So we could make better detectors, but this is the future. Okay, so let me go on. So there are technical challenges that are in this thing, and I put them in a table like this because we're not done by any means. These detectors can be made better, and people have thought about it a lot, and I will just say that there are the directions in which they get better, and they by reducing the quantum noise, for example. These are laser interferometers. You can use squeezed light, which is light that has been tailored so that it's injected at the output port of the instrument. And what it does is it makes it so that you don't get the quantum noise. The momentum noise of the photons in the strain signals, and you at one set of frequencies, and you don't get the position noise at other frequencies. So there's tricks you can play, and we're beginning to play those tricks. That's called squeezing light, but it's still a big problem. There are a lot of things that are still wrong. The thermal noise in the mirrors are causing problems. Charging on the optics, a whole bunch of things still are ahead of us. And we're now looking at other ways to improve the system. These are slow, and let me show you what I mean by that. Here is the curve that is sort of where you'll see, and this is the curve of the performance of the instrument. And I want to spend a little time on this. This is frequency down here, and this is the strain or the gravitational wave measurement, but in frequency units. Let's not get troubled by what exactly it is. But as you go down in this picture, the sensitivity gets better and better and better. And so here is, for example, Virgo, which is that detector in Italy, which is now operating. And in 2019, it had a sensitivity that is this green curve. And this is sort of 10 to the minus 23 strain per root hertz. That's that line right there. Here's LIGO when it made the detection. It's right there. And that's when it made the detection of about 10 different binary collapsing objects. Here is where it is now. And you can see something interesting. We spent 2 years between here and there working on the instrument. We got some improvement at high frequencies, but down here, very little. And it's getting harder and harder to do this. And in fact, here is where we hope to be. This is where the design curve is for what we now have built. That's where we ought to be. And at low frequencies, we're still quite far from it. Near the middle, we're not too bad, but up here we couldn't get all the laser power we wanted to go. And here's a table which I'm not going to interpret for you unless you ask me questions about it. So here is where we think we can get still in the existing facilities. That's sometime in the middle 20s of this century, and with making improvements in various things, using quantum optics, using better, bigger masses and stuff like that. But our real hope is to take this thing into cosmology. And the Italians have an idea. The French-Italian system is going to try to build the Einstein telescope, which is way down here. And the Americans, and so far the Americans mostly, have an idea of how to make something in 2 stages, which is a 40-kilometer LIGO, 40. That's 10 times larger than what we have. And without much work except making it longer using the technology we have now, we would be down here. And if we change the technology, we could get down another factor of about 2 or 3. And that gets you squarely into cosmology. And that would be fascinating. And so here is where, this is the current stage of things. Here is the time. So here's 2015. Here is 2026. Let's stop right here, because this is all we can really predict at this moment in these instruments. We have a way to go yet. LIGO can keep improving. We're now at somewhere in 120 megaparsecs for the measurement of a neutron star binary, for example. And we can make improvements we see to get out to 175 megaparsecs. Virgo, which is another telescope, a gravitational wave detector, which is operating in Italy, is doing well, but not as well as LIGO. I wish it was better. But here is Kagra, which is a thing that's going to be being built in Japan. Has smaller sensitivity, but this network then will have sensitivities out to, maybe hope, somewhere around maybe 130 to 175 megaparsecs away from the Earth for example, neutron star binaries. Now, the thing is that what gets more and more difficult is that if you want to really do better, and if you want to begin to do cosmology with this field, you've got to do a lot better. And that's the idea that we're pushing. Somebody's pushing the slides for me. I'm delighted. Thank you for doing that. And this is an idea that is what would happen if we built a 40-kilometer system. And here, this is a little tough to explain, but let me try. How much time do I have left? You're about to tell me to get off? Okay, I have enough. So this is a little picture of 2 sources. And these are, for example, what we have now is a detector which is O2, or O3, it's a little better than that. And this is the distribution of black holes, which we are already beginning to see these black holes. And if we build a system which is as best as we can with the system we have now, we can get right into the middle of the distribution of black holes at a distance And here's the distance of a redshift, about 3, or even a little more. So we can certainly get into cosmological measurements with a system that is in this region. And that would mean building something that's 10 times longer than what we have now. Over here is the system, same kind of plot, but now for neutron star binaries. And if we build A+, which is that first thing we can still do with the existing facilities, we're in here. We can do a little bit of cosmology, really, with A+, that's the green. But if we want to really do all of it, we have to build this cosmic explorer, which is this 40-kilometer system. And that's this red one. I said it wrong when I pointed to it a minute ago. That's the place if you build the 40-kilometer system, you're out here for the black holes, you're in the middle of the neutron stars, and if you then make that final change in improving the technology in that 40-kilometer detector, you have now encompassed all the black holes we believe are there, and encompassed all the neutron stars that are in the universe. So that's the thing we're pushing ahead with that, because we see the field and the science now that comes out of this thing is really quite spectacular. And we want to be able to do cosmology with using gravitational waves, because it adds so much to cosmology. So I think this is my last slide. Yeah, good. What this is sort of give you a quick summary of where the field is and will be in the next, probably next 30 years. That's probably the best I can say right now. So this is frequency of gravitational waves. Up here is period, expressed in terms of identifiable objects. So 1/10 of a second to 1,000th of a second, minutes, hours, years, age of the universe. And here are the sort of typical strain sizes that you have to get to. We're here with LIGO right now, and we hope to improve it. If you want to get to longer periods, there is the LISA project, which is a space project to look at longer periods, and that will look at massive black hole coalescences, and also small black holes, or small objects falling into black holes. That's one of the most promising areas to really test general relativity. And this is a space-based mission. It's called LISA, the Laser Interferometer Space Antenna. This is a thing that's going on right now, but it's a very limited sensitivity. This is sensitivity getting poorer as you go up this way. 10 to the minus 15, 10 to the minus 5 in H, okay? And this is using pulsar timing, and the idea is, and that's going on now, you look at a set of pulsars in the sky, let's say in the northern hemisphere, and then you look at the ones in the southern hemisphere, and you say, they're all the ones in the north are going a little slower, and the ones in the south are going a little slower. And then you look east and west, and those are going a little faster than they used to. And that's that quadrupolar pattern that you would experience if you were using pulsars as a way of looking for these gravitational waves. And that has a chance of looking for supermassive coalescences. And then there is this thing that everybody knows about, but it's got to be done successfully without getting completely, it got to be done well. And that's the B modes of the cosmic background. And I'll just say this much. This experiment gave a result which we're not sure is right, and I'm quite convinced is not right. But it has an incredible possibility of measuring gravitational waves that come from the very earliest moments of the history of the universe. And those are things during the inflationary period, and that are reflected then in density profiles of the matter that follows, namely the matter when you get decoupling after you begin to see into the plasma. And that gives you a pattern of identifiable pattern of the gravitational radiation. They're called B modes. And that, if that's seen, is going to be one of the most spectacular discoveries ever. Namely because it'll give us something about the energy scale of the universe at the very beginning. And now, that is not going to be done by LIGO. It's not going to be done by any ground-based thing. It's as a direct measurement, but it can be done by doing temperature measurements at a very precise scale, namely nanokelvin from the poles of the Earth. And that's being tried. So thank you.